recitation, voluntaries. 1 p.m. or 3 p.m. practice. Then we have next week. Wednesday. Right. But we do have class on Tuesday, so next week we have class on Tuesday, but after Tuesday is off. Thanksgiving, happy Turkey. And the week after that, what was it, 11, 29 to 30, this quiz. After Thanksgiving, your recitation, the regular recitation Wednesday, Thursday, there'll be a quiz. And today, the plan is to do two things. Series plus induction. And to talk about recurrences plus induction.
You still put the work for that?
That's our plan for today.
Then you might be able to.
Those two things.
Oh wait,
I asked the guys to do it, so I think so a little recap on those series. So here's a series. 7, 13, 19, 25, 31. How do you recognize the series? We look at it and say, what is this? You take the differences, that's a 6, that's a 6, that's a 6, that's a 6. So this gotta be, in terms of ax plus b, right? It's gotta be a linear. We call it arithmetic progression, but it's really a linear generating function that does this. So what is a and what is b here? A's gotta be this difference, right? A is the delta. So this gotta be 6x plus what? 1. Very good. So again, how do I know 6? A's gotta be the delta between them. Right? How about a different one? 4, 11, 24, 43, 68, 99. What is this? How do we look at it and say, what kind of series this is? What sequence? That's a sequence. The series is the sum of them. So the series is the sum from k equal 1 to n of that. 6k, let's say x better, because we have it today. 6x plus 1. That's a series. So the sequence is the actual enumeration, the sum of it from 1 to some number is that. So I could do this, right? 6 times the sum of x from x equal 1 to n plus 1 n times, that is n, right? I can go even further. You guys remember how much this is? The sum of 1 plus 2 plus 3, this kind of sum, how much is that? That was n times n plus 1 by 2 times 6 plus n. How about this one? If I do the differences here, what do I get?
13, 19.
Yeah.
20.
That is exactly this one here, right? These differences. This is the delta. This is the delta, the differences. So this one, I already know that's got to be 6x plus 1. I've done it already, right? So what is this one? This one here is got to be what? If this is 6x plus 1, what is this? This got to be quadratic. If this is arithmetic progression, this is quadratic. So that's got to be some sort of ax squared plus bx plus c. This in here, it's called linear or arithmetic progression. This is quadratic. So I can try to find A, B, and C by plugging in something like x equal 1. I get A plus B plus C, should be the first one, 4. And then I do x equal 2, that's A times 2 squared, that's 4, plus B times 2, plus C, that should be the second one, that's 11. And then I plug in x equal 3, I get A, 3 squared is 9, B times 3 plus C is the third one, 24. I can solve this system and get A, B, and C out of it. Or, I think I told that some people at recitation, right? I could think, hey, I can guess A directly. A, the big coefficient here, I could do it without solving that system. I could say, if this is f of x, if I take the differential, delta f of delta x, how much is that? Anybody knows the differential of this function? A, B, C are constant, they're coefficients. So what's the differential of a degree 2 polynomial?
2ax
2ax
plus b.
plus b. I say 2ax has got to be this 6 in here because the delta is just a discrete version of the differentials, if you think about it. The differences between sequence points, if you remember from calculus, that's just a discretization of the differential. So this is approximately the discrete differential, which means 2a has to be the 6. So a is 3. And if we further move on, I'm going to do that in here. You guys have to figure that out. I get b equal minus 2 and c equal 3. We can verify this kind of equations. How much is 3 times 4? I want to verify this equation right here. 3 times 4, I'm plugging in a equal 3, plus minus 2, that's my b here, times 2, plus c. C is 3. How much is that? 12 minus 4 plus 3. How much is it? That's because instead of solving this system, I smartly guessed 2a equals 6, a equals 3. Once I get a equals 3, this system is a lot easier to solve for b and c. If you don't want to guess like me, a equals 3, you can just solve the system and get a, b, and c out of it. Okay? How about this other series here I have, sequence. So first of all, if I want to do the sum of this, the sum of it will be what? Sum from x equal 1 to n of, I look at it in this form, that's 3x squared minus 2x plus 3. right? Because I've got b equal minus 2 and c equal 3. Do I know how to sum this up? I break it into parts, right? So that's a sum 3x squared, that's 3. Sum from x equal 1 to n of x squared. That's, I'm done with this one. Then I say minus 2 sum from x equal 1 to n of x. And then I count how many 3's I have here. How many terms are in this sum? These 3, how many times is summed up? N times. So that's 3n. So with this one, we know how much it is, right? So 3n is 3n. This is minus 2 n times n plus 1 by 2. This is the same as before. How about this? This thing in here we did last time in class. Last proof by induction was exactly this sum, if you remember. This in here, it's 1 squared plus 2 squared plus 3 squared plus n squared. And that's the last thing we proved last time by induction in class. So this in concise form, this is sum from x equal 1 to n of x squared. And anybody remembers the answer? There was a formula that we proved by induction. Yes?
n plus 1 times n plus 3 times 2n plus 3 over 6.
N times n plus 1, I think. That was for the n plus 1, so this is 2n plus 1 by 6. The formula you just read is for n plus 1, the next one. So if I do these squares up to n plus 1, I get n plus 1 times n plus 2 times 2n plus 3 by 6. But for n is this, right? So we already have this from last time, so I'm going to plug it in here. N times n plus 1 to n plus 1 divided by 6. And I have a coefficient in front of it, I have this 3, right? So here I got a formula for how to sum up this sequence into a series. Who's following me? We have any questions about this? This is easy stuff. Here's another one. 3 by 1, 3 by 2, 3 by 4, 3 by 8, 3 by 16. The general form here, so I'm going to ask you, what is this series? How does the general form looks like in here? This is different than those two. This is a quadratic series, this is a arithmetic progression or linear. What is this one? It's 3, obviously. Everybody has a 3 times. How is this fraction progressing?
1 over 2 to the x, where x starts at 0.
Sometimes we say k, depending what you like for an index. Some people call this indices I, k, x, whatever letter you like for the index. But nobody uses a, b, and c. So for indexes, people use x, k's, i's, but when you see n's sometimes, but a, b, and c are typically constant coefficients. So don't use a for an index. Okay? That's the general form. This is a geometric series sequence. In my country, we don't call them sequence and series. We use the word series for both the sequence and the sum. That's why I'm a little bit confused about this. But in here, we call them sequences, the enumeration. And if I sum it up, if I get a series, I get sum from x equal 1 to n of what? 3 times 1 over. This is actually starting from 0, right? That's actually something you have to pay attention. Every time you index something, like in here, you look at the first term, you say, this is corresponding to x equal what? Right? This is x equals 0 because this 1 is 2 to the 0. In some problems, this would be 2 starting at 1. In some problems, we start at 0. So how do I sum this up? From 0. 2 to the x. The 3, of course, is a 3. And then I have, I'm going to call R here the ratio 1/2. This is R at 0 plus R at 1 plus R at n. You guys remember the formula for this? There was a formula. And I have an R, and I start from 0, the geometric series, 0, 1, 2, up to n. There was a formula here. How much is that? Anybody remembers that formula? R to the 0 plus R to the 1 plus all the way R up to R to the n. Yes?
R plus 1 times R to the n. Yeah, no, I got it wrong. Over, isn't it over R plus 1? Or minus, yeah, that's enough.
Right? That is true if R is not 1, of course. If R equal 1, you can't do this, right? You divide by 0 here. That's not allowed. We proved this last time in class. We were saying if you multiply R minus 1 with this guy, there was some reduction going on, and you get R at n plus 1 minus 1. Remember? So that's how I can sum up. In my case, of course, R is 1/2. So this is 3 times 1/2 at n plus 1 minus 1 divided by 1/2 minus 1. Because this R for me is 1, 2. In a different problem, this R might be 2 or 3 or 0.3 or something. This works for every R if it's not 1. The only R for this formula doesn't work, it's R equal 1 because that would be a division by 0. But if R is 1, how much is this sum? If R equal 1. Close. How many terms are here?
N squared.
How many terms are here if I start from 0 to n?
N plus 1.
N plus 1, and all of them will be 1. So for R equal 1, this is just how much? N plus 1. So if R equal 1, that sum, R0 plus R1 plus R to the n is just n plus 1. If it's not 1, then I can apply this formula. Good. So we've gotten somewhere so far. Let's see. Let's prove some of this stuff by induction. So we proved this formula not with induction. We did it with arithmetic. And we proved this formula here with induction. This sum here being n times n plus 1 plus n plus 1, that was last time, was induction. And we proved this formula here without induction. I just multiplied this with that, and I've got that with some reduction. So now, let's see if we can redo some of this proof by induction. So I've already done a few induction proofs at recitations, and we're gonna do 2 or 3 more now. And then you guys have a paper for Tuesday, the recitation paper that has more induction proof in it. So here's one induction proof. I want Sn to be 1 plus 2 plus 3 all the way to n. This one here. So in concise form, this is sum from k equal 1 to n of k. And I want to show that this is n times n plus 1 by 2. I know we already showed that. Anybody remembers how we show it? We wrote this sum this way, and again, we wrote it backwards. And we add up column by column, and I got n times n plus 1. We divide by 2 because we added twice. But now we're going to do it by induction. So base case, n equal 1. S1 is, what is that for n equal 1? It's just 1, right? And this side here is 1 times 1 plus 1 divided by 2. Is that true? So in the base case, we plug in mechanically the value of n. And then once, after we wrote it down, we ask, is it true or not? Is it true or not? Good. And now we have an induction step. In the induction step, we always write down what is it that we're going to prove. What is the implication? In here is that if Sn is n times n plus 1 by 2, so I'm assuming I already know this for n. Then I want to prove Sn plus 1 is what? I have to write that formula down for n plus 1. What is that? What is this formula for n plus 1?
N plus 1 times n plus 2 over 2.
Right. So how do we show this? Now, that's not a proof. That's just saying this is what I want to prove. Every time you do an induction step, you state first what it is that you're proving. So how do I do this? Well, Sn plus 1, I say is just Sn plus n plus 1. Right? If you look at this sum, who is Sn plus 1? Is the sum all the way to n plus 1, right? But the sum all the way to n plus 1 is the sum all the way to n plus the additional term. How many people follow me here? Good. So now I'm using the induction hypothesis here. I'm saying I know already Sn. That's from here. So this is n times n plus 1 by 2 plus n plus 1. I replaced Sn with n times n plus 1 by 2 from induction hypothesis. We call this induction hypothesis, which is the same as premise. So in this implication, we assume we already know this. It's like knowing from n, moving to n plus 1. Now what do? Remember from recitations? When we down to this, we take a moment and make a plan. This is what I have and where I'm trying to get. Where is it that I'm trying to get here? I want to manipulate this with algebra now, right? To get where? What's my final result that I want to get?
n plus 1 times
This, right? So I want to make a plan. Before starting writing algebra, what is in here that looks like that already?
n plus 1.
Who is in this product that looks like I already have it, kind of?
n plus 1.
The n plus 1 part. Who is in this product that looks like I don't have it, or it's not obvious where it's going to get?
n plus 2.
N plus 2. N plus 2 has to come out of calculations. So if we have n plus 1 already, actually I'm going to force n plus 1 by 2 common factor. Because I see the n plus 1 by 2, I see an n plus 1 by 2 here. What's left of this term, the first one? N, right? What's left of the second one?
2n.
2, because I put the n plus 1 in the front, and I only have one n plus 1, but I force this 2, so I have to put it back. Right? 2 times this has to give me n plus 1. See how I got n plus 2? That's exactly the term that I was missing. So that actually, it's easy to see. This is the same. N plus 1 times n plus 2 by 2. That proves the induction step here. The induction step allows me to move from 1 to 2, 2 to 3, 3 to 4, so on and so forth. It tells me the Sn is this formula all the time, assuming I got a base case. How about that geometric series? Sn is r to the 0, r to the 1, r to the 2, r to the n. In concise form, that is sum from k equal 1 to n of r to, from k equals 0, sorry, r to the k. I want to prove, let's remember the formula. I want to prove this is r at n plus 1 minus 1 divided by r minus 1. That is this formula right here. I want to prove it by induction, not by manipulation and reductions. And I'm going to do this if r is not 1. If r is 1, obviously this doesn't exist. You can't divide by 0. So this works. R is a constant here. It's not the summation index. The summation index is the exponent, which is the k. So how do I do this by induction? I have a base case. What is the base case? N equal 1. Actually, let's try 0 first. For n equals 0, who is S0? If I do this sum, but only for 0. I get r to the 0, right? That's it. And who is this? For n equals 0. 0 plus 1 minus 1 divided by r minus 1. Is this true? What is 0, r at 0 plus 1 minus 1? That's r minus 1 divided by r minus 1, that is 1. And how much is this? 1. Good. How about for n equal 1? I'm doing another base case, not necessary, but sometimes doing few base cases helps. S1 is R0 plus R1, right? R to the 0 plus R to the 1. That's supposed to be R at 1 plus 1 minus 1 divided by R minus 1. Okay. I just plugged in mechanically n equal 1 in here. Is that true? We don't know, huh? So that's 1 plus R. R to the 0 is 1, right? And this is R squared minus 1 divided by R minus 1. You guys remember that formula? R plus 1 times R minus 1 is R squared minus 1? Or in general, A plus B times A minus B equal what? A squared minus B squared. Right? So the formula that applies here is A squared minus B squared is A minus B times A plus B. And if you apply that formula for R and 1, you get this. So this checks out too. What is the induction step here? First, I write down what I'm going to prove. If Sn is R to n plus 1 minus 1 divided by R minus 1, I want to prove that Sn plus 1 is what? What is this formula for n plus 1? How's that going to look like? If I am to read this formula, but not for n plus 1, what do I get? R to the what? N plus 2 minus 1 divided by n minus 1. So let's see if we can make this proof. Who is Sn plus 1? I applied this trick I've always applied. It's a sum of things, but a lot of these things are already part of Sn, right? Sn, it goes to the up to the power n. Sn plus 1 just adds one more term to it, right? If you think of Sn plus 1, it's still R0, R1, R2, Rn plus, what's the last term in that sum? So this is just Sn plus R at power n plus 1, right? What's next? How do we continue this? What's the next step in here?
Pause.
What?
Think.
We first write Sn. We already know Sn from induction hypothesis. So that is R at n plus 1 minus 1 divided R minus 1 plus
Too early.
R at n plus 1.
Damn.
Right? R at n plus 1 is the new term. Sn is this guy I have from before. So now I pause and think. How do I get from here to here? What looks like I already have? R minus 1. The other ones, not sure yet. I don't see an obvious way to get an R at n plus 2. R at n plus 2, how is this depending on R at n plus 1? It's just multiplying with one more R, right? But it's not obvious clear where I get the one more R. So let's go by what we have, which is 1 at R minus 1. Common factor. Because this one's going to have to appear in the formula. What is left from this term if I take out the 1 to the R minus 1? Okay. How about in this term? In this term, there was no 1 over R minus 1. Right? I forced it out, but there was no such common factor in here. So what do? This plus R at n plus 1 is R at n plus 1, what I had there. But now I have to put this back, right? I force it outside, like I divide by 100. I have to multiply back by 100. So that is times R minus 1, right?
Yes.
You guys see this? Where is this coming from? Well, I force it out here, so to get back the term that I originally had, R at n plus 1, I have to put back the R minus 1 in it. So now what is this? 1 over R minus 1. What is this up here? R at n plus 1 minus 1 I open the parenthesis here, right? How much is r at n plus 1 times r? How much?
R plus 2.
And how much is r at n plus 1 times 1?
R minus 1.
Aha. This guy goes away with this guy. And what do I have left? R at n plus 2 minus 1, which is exactly what I needed on top here. Right? Of course, I also have the 1 at r minus 1, which is this. So I could write this as 1 at r minus 1 times r at n plus 2 minus 1, which is the same. How many people follow me here? Right there. So I can do this kind of proof by induction. If I don't know how to multiply this, that's going to work too. Let's do one more induction proof. Some stuff it's easier by induction. Some stuff it's easier with direct calculations. You have to have practice to figure out which one it's easier induction and which one it's easier just write it, work it out directly. I have here one that says, see where that is. With some of the odd numbers, I think. Yeah. So I have Sn is the sum from k equal 1 to n of 2k minus 1. That's the odd numbers. So it's the sum of odd numbers. Right, that effectively, if I write it down in open format, 1 plus 3 plus 5 plus 7 plus 9 plus the last one is 2n minus 1. I want to prove that this sum is actually n squared. Let's see. Base case. N equal 1. What is S1? If I just have one term in here, right? Because this sum for n equal 1 will contain just one term. What's the first term? It's just the 1, right? And how much is n squared? 1 squared, is that true?
Yeah.
Right. Let's try another one, n equal 2. Who is S2? 1 plus, what's the second term? 3. And who is n squared? 2 squared. Is that true? How about we do an induction step here? Sn is n squared implies Sn plus 1 will be what? What is this formula for n plus 1?
N squared.
I replace n with n plus 1, what do I get in that formula in there?
N plus 1 squared.
Are we all following how this goes as a principle? I mean, there's calculations, and you can be wrong on calculations, and everybody was wrong on calculations, and I made so many mistakes in calculation when I was a student. The professor already knew, this guy's gonna get it wrong, okay? Virgil, I was famous for getting everything conceptually right, but always mess up the calculations at the end. So our math teachers would ask me to figure out how to solve it, but always somebody else, they say, sit down, somebody else, figure out the calculations now. Right? So I'm not that interested in calculations. I'm interested if you can follow the plan. All these have the same plan built in, right? The different series, but the plan is the same. So how do I get Sn plus 1 here? Who's Sn plus 1? It's just Sn plus another term, right? What's the last term that Sn adds? I need to add to Sn the last term. What's that last term? If I have to write down Sn plus 1 here, will be the sum from k equal 1 to n of that 2k minus 1. That's the same, but there's another term here, right? which is the term for k equal n plus 1. What is that term?
2 times n plus 1 minus 1.
2 times n plus 1 minus 1, right? So 2 times n plus 1 minus 1. Okay, what's next? I have to replace Sn with what I already know. So that is n squared plus 2n plus 1. Right? Because Sn is n squared. And then 2n plus 2 minus 1 is 2n plus 1, right? Everybody can see this? If I open the parentheses, I get 2n, let's write it down. 2n plus 2 minus 1. 2n plus 2 minus 1. So this is n squared plus 2n plus 1, right? Now I should stop, make a plan. How do I get from here to here? But that's obvious. Right? This, everybody knows this is n plus 1 squared. That's just the formula. People know this formula, a plus b squared? What is it?
B squared plus 2b.
What a minus b squared? How much is that? A squared plus b squared?
Minus 2b.
How about a plus b cubed? A cubed plus b cubed plus 3a squared b plus 3ab squared. You guys gonna have to, I know it sounds like, oh my God, but you know, fluency into those formulas will help a lot during the final exam, you know, which is another marathon of 2 hours. How fast can you write? Right? So if you know these formulas, it will help to get it done in 2 hours. All right. Anything else? Induction proofs here. There's a bunch of them. I think you're gonna get the rest done by yourself. I want to do another series in here. Sn is the sum from I equal 1 to n of, let's say k, because we use k, or actually let's use I. Sometimes I use x for the index, sometimes I, sometimes k, sometimes n, but never ABC. ABC stands for coefficients, those are constants. So I'm going to use I in here. I've used k before. I times I plus 1. So if I'm to write that in like enumeration, what is this? You gotta love the lights in
They
this
just
room.
came out.
What's the first term in here? 1 times 2, right? What's the second term? If I'm to write down this explicitly.
Oh, 2 times
2 times 3. What's the next one?
2 times 3.
What's the general one? That's I times I plus 1, right? Of course, because that's right there. Plus, what's the last term for I equal n?
And times n.
Uh-huh. This formula comes out to 1 minus 1 over n plus 1. Or if I am to manipulate this a little bit, that's n divided by n plus 1, right? Because n plus 1 minus 1 equals n plus 1. That's what I want to prove, that that is equal to that. So I can start with the base case. N equal 1. So who is S1? It's 1 over 1 times 2, right? Who is that? 1 minus 1 plus 1. Again, I mechanically replace this n here with 1. Is that true? 1/2. How much is this guy? 1/2. 1 minus 1/2. It's 1/2. Good. Induction step. If Sn is 1 minus, let's use the other form, maybe it's easier. N divided by n plus 1. We want to prove Sn plus 1 is what? How do I read that formula? But not for n plus 1. Say I use this. Those two are the same thing. I can use whichever I want. How do I use this here? for n plus 1 now. What is this? N plus 1 divided by n plus 2. I'm not sure which one's easier. Maybe this is easier, but I hope you guys see that this is exactly the same thing, the simple addition. Okay, so who is Sn plus 1? Is Sn plus, what's the next term? Right? Obviously, Sn plus 1 will do all these terms, but it's going to add one more. Which is that last term that it's going to add here? Well, I have to be in that form, right? So it's 1 over what? All the terms in here are 1 over a product of consecutive value, right? So the last term, if I want one more, will be what? What's the next term here? N plus 1 times n plus 2, right? Okay, next step, I replace Sn, n plus, I already know this Sn, sorry, it's coming from here. This is n over n plus 1 plus 1 over n plus 1 plus n plus 2. Then what? What's next? We stop. Okay? Even during the exam, rushed up, we stop and say, this is where I'm at, this is where I want to get. Right? What looks like it's like there and what looks like it's not like there. Yes.
The n plus 2 is already in the denominator, and n plus 1 goes to
Right, the n plus 2 is the denominator here, but not here.
Yeah.
And n plus 1 is the denominator in both that looks like nice, but it's not in the final result, right?
We have an n and a 1 at the top.
Right, what would be the point of taking out 1 over n plus 1? Can I do this? Would you do this 1 over n plus 1 common factor because it's in both? No, because it's not in this result here. Right? So, I mean, that's correct, but it's not going to help that much. What would help to take as a common factor, to force a common factor?
N plus 2.
1 over n plus 2 will be a more desirable common factor because that's in here. Right? So if I do that, this guy doesn't have it. So I do what? N over n plus 1, but I have to put back what I divided with because it was not there. So this is n plus 2 here. I have to put it back. I have to multiply with what I divided. Plus, now what's left of this? I got 1 over this product, but I took out the 1 over n plus 2 in the front. So what's left of it?
1 over n plus 1.
Okay, 1 over n plus 2. Let's calculate. Actually, I have an n plus 1 here, but again, I could take out the n plus 1 common factor. Still not helpful because it doesn't appear in the result. What's the point of doing that if I don't have it in the final result? So I'm going to leave it here for now, n plus 1. What is this calculation here? N, those I can add because they have the same denominator, right? Two fractions with the same denominator, I can just add the numerators. This is n squared plus 2n plus 1, right? N squared plus 2n, and the 1 coming from here. Now, I applied that formula that we just said we should know. That is 1 over n plus 2 times how much is that? That's n plus 1 squared divided by n plus 1, right? This thing here is n plus 1 squared. So, of course, now I get rid of this n plus 1, I get n plus 1 divided by n plus 2. Because n plus 1 squared divided by n plus 1 is this n plus 1. This is what I want to get, so I'm done. I want to do this series in a different way. I'm going to get the same result, but now with induction. This is a very important series because each term, 1 over I times I plus 1, is actually 1 over I minus 1 over I plus 1. Each one of these terms here, take the generic term, is actually a difference between 1 over I and 1 over I plus 1. This is very easy to see, right? If I multiply this guy with I plus 1, right, why is that? Because this is I plus 1 divided by I times I plus 1 minus I divided times I plus 1. which is 1. If you do this, you get the 1 over I times I plus 1. Because this is a difference of terms that look the same, just iterated by 1, as in a over some 1 over some a n, this is 1 over a n plus 1. This means it's a telescoping series. So there's a much faster way to do this series, which is, what happens if I write all of them that way? How much is going to be 1 over 1 times 2? That's 1 over 1 minus 1 over 2, right? According to this formula. And that's true, right? What's about the next one? This is 2 by 3. This is going to be according to this formula who? 2 by 3. If I apply this formula here, what is this difference? That's 1 over 2 minus 1 over 3. Is that correct? 1 over 2 minus 1 over 3 gives me 1 over 6? What about the next one, which is 1 over 3 by 4? If I apply this formula, what do I get? 1 over 3 minus 1 over 4. So this is that, this is that, this is that. How about the next one? That's 4 by 5, right? That is 1 over 4 minus 1 over 5. Is that true? 1 over 4 minus 1 over 5 is 1 over 20? Right, because 5 minus 4 divided by 20 is that. How many people follow me here? Hands up so I can see them, please. Plus, if I apply this for the last one, which is 1 over n times n plus 1, I do the same. It's 1 over n minus 1 over n plus 1. Right? Why is it called telescoping? Where's the telescoping name coming from? What does it mean? Telescoping.
Famous.
What telescoping means in here?
Don't the terms cancel out?
That's telescoping. Terms cancel out. This 1/2 goes away with a 1/2, minus plus, 1/3 with 1/3, 1/4 with 1/4, 1/5 with 1/5. This n with this guy here. And the n is just the first term minus the last term. 1 minus 1 over n plus 1. Which is no surprise exactly what we want to get here. Telescoping series is a series that can be written as a difference in such a way that when you add up those differences, the minus from here cancels with the plus from the next guy, and the minus from the next guy cancels with the plus, and so on and so forth. So all of them goes away except for the first one, has nothing to cancel on, and the last one, nothing to cancel on. That's why we get 1 minus that, which is, of course, the correct answer. Telescoping series. So most of this stuff can be proven in two ways, either with some interesting mathematics formulation calculation, or by induction. I want to do here an induction proof that you have in your recitation paper. The one that I gave you this week. That is I forgot what that is. Oh, here. If x is bigger than minus 1, or 1 plus x is positive, that means it's the same thing, then my statement here, Sn, is logic. It says 1 plus x x in here is a real number, and it's fixed. It's a constant. That could be any number. 1 plus x at n is at least 1 plus n times x. That's an inequality. And we want to prove by induction over what variable? What's going to be the induction variable that moves from one to the next one in there? It's n, the ones that we're proving. X is a constant, which can be any real number, for example, 1.75, or 2.33, or minus 0.2. N is a natural number. So this statement of logic is true or false, of course. And the only difference between this and those summations is that Sn is not a sum in here. It's not a number. It's just a statement, true or false. But the rest of the proof goes the same. Base case, n equals 0. How do I write that? S0. What is it? 1 plus x at 0 is bigger than or equal with 1 plus 0 times x. Is that true? How much is 1 plus x at 0? 1. How much is 1 plus 0 times x? Let's try another base case, n equal 1. Who is S1? 1 plus x at 1 bigger than 1 plus 1 times x. Bigger or equal? Equal is fine. How much is 1 plus x at 1? 1 plus x at power 1 is how much?
1 plus x.
1 plus x. And this is?
1 plus x.
Okay, how about induction steps? First, I write what I want to prove here. What I want to prove is that if 1 plus x at n is bigger than 1 plus nx, that was my Sn statement. I want to say that from here, I can prove Sn plus 1 statement, which is what? How do I read this implication for n plus 1? What would this be? This inequality for n plus 1 is what?
1 plus x to the n plus 1. Is
Right.
then equal to 1 plus n plus 1 times x.
So this is my premise here. I can use this. I can assume it's true. Like before, I knew what Sn is. In here, I'm assuming Sn is true, which means this holds. And I want to prove this one. Okay? So I'm going to start from here. 1 plus x at power n plus 1. How do I get this in terms of 1 plus x at n? Right? That's the same as I was asking before. How do I get Sn plus 1 as Sn plus something or times something so I can use Sn? Well, that is 1 plus x at n times what? How much do I need to multiply with to get 1 plus x at n plus 1? So this is the orange at power n plus 1. That's a orange, the same orange at power n times the orange, right? Okay. Well, I already know something from the premise. The premise is telling me that this guy, it's bigger than something, right? So that's bigger than what? 1 plus x at n is bigger than 1 plus nx. So this is where I'm using the premise. This part is bigger than this part. And I still have the 1 plus x thing. That's the one that I have here. I'm just putting it here. Well, let's see how much this is. Is what? 1. I'm opening the parenthesis. 1 plus nx, right, plus x, plus how much is nx times x?
X squared.
Now I pause for a second and say, okay, this is what I have, this is what I want to get. How much is this guy actually? I'm going to just make a plan. How much is it if I open the parenthesis? 1 in the front plus nx plus x, right? So here's what I've got, and here's what I'm trying to get. Am I already there? Can I say this is bigger than that?
Yes.
Why?
Because an x squared will always be bigger or greater than or equal to 0.
This is a positive value. Even though x can be negative, I didn't say x is positive, I say x is bigger than -1. So x minus 0.5 is a valid x. X squared is guaranteed to be positive. So if this is positive, it's bigger than that, I'm done. Because this is what I wanted to get at. How many people follow me with this proof? Hands up so I can see them, please. Questions? Yes.
Can you go over the, like, how
This?
you set up the equation?
Why is
So
this
like
equal
when-
that
when
times
the-
that?
Yeah, yeah.
So my plan was to relate the statement is Sn plus 1 to the statement I have in Sn. So I wrote that down, 1 plus x at n, and then I figure out what else do I need to multiply to get this, because this has to be correct mathematics. I can't just put whatever I want here. So I figured, if you think of this as a number, 1 plus x, that number at power n times itself is that number at power n plus 1.
Yeah. Wait, why is, no, like I understand that math.
This is okay.
Then,
Then next,
yeah.
why is this bigger than this? Anybody? Why I say this is bigger than that? Where is this coming from?
No, I meant like how did you set up that equation? Like,
This?
Where did you get it?
The two parts of it, how did you get there?
This?
Like that and
1 plus x is the 1 plus x. This is from before. This 1 plus x just moved here. I didn't touch it. The only thing I did, I replaced 1 plus x at n. I say that is bigger than that. Where did I get that from?
the beginning
Premise.
premise.
The premise, which is this.
And then just multiply
Right.
both sides with it.
So this is the same, but this in here, from here to here, that was the premise. I say, I knew this is bigger than that from the induction hypothesis. One more roll of hands. Who's with me here? It's absolutely critical that we understand how induction works. It works the same for logic statements as it works for sums. This is a true or false thing. The other ones were calculations.
What about the case when we get to say this step and then it turns out that the premise is false? How does that work? Like,
No, no.
Is there a case where we
That-
disprove it?
No.
Okay.
Premise is true. In induction step, we start with a true statement for a base case, 0 or 1 or 2, whatever we want to start, maybe 7. But then we say from there, the induction step, from 7 moves to 8, 8 to 9. So we always assume the premise is true.
No, but like the original, for example, we say the Sn at the top, like the thing we're trying to prove. What if we try to disprove it? Can we disprove by induction as well?
No. I mean, it may be that what you're trying to prove is false, and that means somewhere in the proof you must be wrong. If you can get the base case to work correctly and the induction step, it means you prove it. You can't prove something that's wrong, so there must be a mistake somewhere. We can prove other statements by induction or otherwise, but the general sort of thing here is, first we prove something is true in the early beginning, and then we prove by the induction step it's true everywhere from there. Yes?
If your premise is true and you're multiplying both sides of the premise by the same thing, can you just then at that point say that it's true?
Yeah.
So you don't
If you
need to go
multiply
on.
by a positive value, right? So you what he's saying, start with Sn, 1 plus x at n is more than 1 plus nx, right, I think? And you say multiply both sides by 1 plus x, right? That's what I actually did. So then this is 1 plus x at n plus 1, bigger than 1 plus nx times 1 plus x. And this turns out to be bigger than that, right? So you can start with the premise as a given thing and start manipulating it until you get to what you want to do. That's an absolute correct way of doing it. You start with the premise, and then you, via manipulations, you get to, the same thing can happen for sums, right? Instead of doing it this way here, I could say if Sn is 1 minus 1 plus n plus 1, I start with the premise. Then I add to both sides what I need to add, this term, 1 over n plus 1 by n plus 2. And then I say Sn plus that is 1 minus 1 plus n plus that. This turns out to be Sn plus 1, and this is going to end up what I want to end up with. This way of doing it is a little bit more difficult because you start with Sn. You have to be creative to know where you want to go. How do you know to multiply with 1 plus x? Or how do you know to add exactly this term to it? In here, what I was proposing, which is the same thing in terms of calculations, to say you start with something from Sn plus 1, but you immediately try to relate to Sn. Right? So I put Sn and I say, how much do I need? I didn't come up with this 1 plus x without any intuition. This came up as the ratio between those two. And then I try to work it out. Same thing in here. I write Sn plus 1 as a function of Sn, plus this, it's the difference between them. I didn't invent it. And then I try to work out the answer. We have one more series to deal with. That's the honors series. I have one more series to deal with, which is the series, the harmonic series. This doesn't have a closed form. I can't give you a formula for exactly what it is. Like these other formulas I showed you, there was always some formula, n times n plus 1 by 2. This doesn't have a closed form. But it has a very good approximation. The conclusion we want to get at is that Sn is approximately, anybody knows what this is? Ln? Ln of n. That is logarithm base e of n plus a constant. The constant is about 0.577. It's called Euler's constant. We don't care about the constant, 0.577. That doesn't matter for us. What we really want to show here is that that's a little bit too hard, even for master students, to show that. But what we want to show is that Hn, I call it H. Hn, this guy. Hn minus the natural logarithm, this thing, is between 0 and 1. So we're going to say, okay, we don't know about that constant, what is it? And we don't even want to show exactly it's convergent. The difference converges to this constant. That is true. We don't care about converging to a constant. We just want to show that when n grows, because this is true for any n, when n becomes very big, this difference is somewhere between 0 and 1. The truth is the difference is actually exactly 0.577. And the more n grows, the more this difference gets exactly to be 0.577. There's a limit there, if we remember calculus. The limit when n goes to infinity of this difference is exactly 0.577. There's like 50 decimals to it. But in this class, we don't care about getting exactly to that value. What we care is to show this is somewhere between 0 and 1. Even that is a tricky thing to do. What we need for this, the actual magic to make this happen, where is it? It's somewhere in here. There is an inequality. That if we be smart enough, we could prove it. if we'd be smart enough, I'm not that smart to prove that inequality. So we're gonna start saying, I don't know, I show you something magic, right? So that's magic. There you go, Harry Potter, right? I know, I don't want to do that. I don't want you guys to feel like that. Wait a minute, how do you come up with that, right? I came up because I know calculus, and we don't want to teach calculus now. But we want to do two things. We want to say, if we would know this, right, what would we do with it? Assuming we know, how would we use this stuff? And then we want to say, okay, now that we discover how useful this is amazingly useful. Anything that has to do with harmonic sums or logarithms comes out of this inequality. So this is the backbone of defining E. In order to get to E, to even take logarithms to start with, or exponentials, this is essential. So let's assume it's true, right? And say, what can we do with it? Well, if we assume it's true, I'm going to write it as 1 over n plus 1. It's smaller than the logarithm. This is n plus 1 divided by n, right? Inside the logarithm there? 1 over n. And now, how much is the logarithm of a fraction?
So you can subtract them. Right?
How much is the logarithm of a fraction? Anybody knows logarithm of a by b?
Logarithm of a minus logarithm of b.
Logarithm of a fraction is the logarithm of a numerator minus logarithm of denominator, right? Another useful formula. Any logarithm, not just the natural one. Log of a by b is log a minus log b. How about the product? Log of a times b. How much is that?
Log A plus log B.
This is actually the same formula with 1 over b. Okay, so I can write it that way. Natural logarithm of n plus 1 minus natural logarithm of n. This is the same formula. I didn't change anything other than writing the logarithm as a difference, which is exactly true. I didn't make any approximation here. The logarithm of a fraction is the difference between logarithm of numerator, logarithm of denominator, right? Now, this is a telescoping thing, right? If I sum up a bunch of this stuff, it's just like before, it's going to cancel out. So let's do that telescoping. I'm going to sum up from n, I'm using n as an index here, from n equal 1 to some big N. I'm going to sum up the left side, 1 over n plus 1. It's smaller than the sum. When I sum up the inequalities, I use the same sum everywhere. So what I'm saying is an apple is smaller than an orange, smaller than a pineapple. Then the sum of these apples is smaller than the sum of oranges, smaller than the sum of pineapples. That's what I did here. This is the telescoping, right? If I'm to write this up, actually this in here, it's very close to my h. Is this exactly h n plus 1, or is missing something? Hn plus 1 is the sum of 1 over 1, 1 over 2, 1 over up to what term? H of n plus 1. What's the last fraction in there?
1 over n plus 1.
So this is 1 over 1 plus 1 over 2 plus, what's the last one?
We didn't start at 1 over 2.
Right, so I got almost all the fractions, but I got the right one right. 1 over n plus 1 is there, h big N here. But I'm missing the first fraction, right? This starts at 1 over 2, and I'm supposed to start at 1.
Right.
So I have to take that out. So this is h n plus 1 minus 1, right? Do we see this as h n plus 1, which is this sum here? It's exactly the sum, but it's missing the first one. Smaller than, this is going to telescope. If I'm write this down, this is going to be what? Log of the first term, log of 2 minus log of 1, right? Plus log of 3 minus log of 2, plus all the way to what's the last term? Log of n plus 1 minus log of n, right? I wrote this series literally term by term. So how is it telescoping? Who's going away with who? Plus log of 2 here goes away with who?
Minus 1.
Minus log of 2. This with this. Log of 3 will go away with log of 3 from here. Log of n will go away from something from here. So what's going to be left of this telescoping series? Who's going to be left? Only the beginning and the end, right? Log, this is the natural logarithm, so I'm going to put natural logarithm. I shouldn't have said log, 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 log. It's ln, 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 ln everywhere. Let's say ln. Nice to have an erase marker. You can do this on the fly. Use a nice pen. Boom, you cannot do it. So I have a whiteboard at home in my office. I have an office at home. Because of that, I don't like erasers. I like those markers so I can use my hand as an eraser. That's how I grew up. That's what I know how to do.
What if you want to save what you wrote? Do you
Take a
like
picture.
save that?
Take a picture.
Okay, so back to telescoping. Log of n plus 1 is from here, but what's left from here? How much is log of 1?
0.
This is 0. Okay, so that's minus 0. But how about on this side? How much is the sum of n to n of 1 over n? That's exactly hn. So what we have shown here is that h of n plus 1 is smaller than the logarithm of n plus 1, right? It's smaller than hn. H big N. That is true for any n. Right? So we didn't just show it for a particular n. We show it for any n. Because I could do this series up to whatever n I want. 100, 101, 102, 300, 3000, any n I want. So I want to write the same relationship here for the previous guy, h, not n plus 1 and n, but n and n minus 1. How would that look like? hn smaller than? If I replace big N here with n minus 1, the previous one, what do I get? Because this is true for every n, I can replace the n with any other n I like in here. But like 2n if I want, or 3n. How much is this if I replace it with n minus 1? ln of n, right? And how much is that?
HP n minus 1.
Oh, we missed something here. That's not possible. This is bigger than that. We missed this minus 1. There's a minus 1 here. Right? So this is minus 1 plus. Okay? Everybody can see this? There was a minus 1 here. So that minus 1, it's in here. How much is going to be this when I replace it with n minus 1? So now, let's see what I've got. What I want to get is to this. Let's see. Did I prove already that hn minus log of n is bigger than 0? So those two, I think, give me this inequality here. The difference between h and log n has to be between 0 and 1. One is in here, the other one is in here. Anybody can see that? So from the first one, I get that hn is bigger than logarithm of n plus 1, right? Which is of course bigger than, let's say, ln. ln of n. The logarithm is an increasing function. So hn is bigger than this logarithm. That logarithm is bigger than ln, which means the difference between this hn minus the log of n is positive. That's one, that's the left side. And from here, the second one, if I manipulate these things around a little bit, hn minus 1 minus this ln, I move this, I'm looking at this, the left part here, minus ln of n is more than, if I move this term here, what do I have on the right side? 0, right? But now if I move the minus 1 on the other side, I got hn big N minus ln of n smaller than, what happens if I move this one here? I get 1, right? I know this is not as serious like the other ones we did, okay? Even master students will have a little bit of hard time here. But it's not impossible. How many people follow me? Let's do it again. Let's recap it again. I hope we all got this because we telescoped this difference of logarithm and we got to this thing here. What we did after that was to say, if that's true for n, it's going to be true for n minus 1. So that's the same exact expression written for the previous n. And now from this, we got hn bigger than the ln of n. That's the 0 part. And from this one, we got hn minus ln of n smaller than this 1 here. So that's saying hn minus ln of n is smaller than 1. I know this is something you might have to sleep on. What is required in this course is to know this. The difference between the harmonic sum and the natural logarithm is somewhere between 0 and 1. You don't need to know it's actually a constant, but that'll be useful for some approximations. You don't need to know the proof, but you need to know that the harmonic sum is the natural logarithm. About there. It's not exactly the natural logarithm, but it's plus some small constant. Both these things goes to infinity. The natural logarithm becomes infinity when n grows. The harmonic series becomes infinity when n grows. But they grow very close together. They're always within 0.577 of each other. Okay? So that's what we proved here with the telescoping series of logarithm. But it's not a complete proof. Why? What's the part that was, okay, magic? Right? How did I come up with that? Anybody has an explanation for why this is true?
No, it was literally magic.
Magic, right?
Yes.
Well, let's get at it. Let's see if we can elucidate that magic. Now we go into the PhD realm. No, not quite. It's not that bad.
Yeah. Yeah.
I'm going to do a little plot. I'm going to plot a few things. This is the value 1. This is the value n plus 1 divided by n. This is the value n divided by n plus 1. I should say big N, because I use big N today. Big N. And this is 1. Please observe that n divided by n plus 1 is smaller than 1. That's why they appear in this order. What I want to do here, let's do this a little bit so we can see it here. n divided by n plus 1. This is not at scale, n divided by n plus 1, it's very close to 1 for n equal 100, but in order to see this better, I'm going to do it not at scale. Not at scale. What happens to the logarithm? I'm going to plot the logarithm function. So, actually no, I'm going to plot a different function. I'm going to plot this function f of x equal 1 over x. That's not a logarithm. So how much is f of 1? F of 1 over 1, how much is that? 1. It's right here. And how much is f of this? How much is the inverse of this? N plus 1 by n. Is this, right? So if I do like a plot, it's here, that's a value, that's f of n plus 1 by n, and this in here is f of 1. So this function, I think you guys know, goes like this, right? 1 over x. So I should write on it, f of x equal 1 over x. Okay? I also have here a constant at 1, so that's flat. And I have another constant here at n by n plus 1. What I would like to say, the area under f of x, so I say area under f of x in this interval. This area is this, right? That's the area under f. It's smaller than the area under 1. That's the whole rectangle. You guys agree with me? The area under this curve is smaller than the area of the whole rectangle. But it's bigger than the area under this value, n by n plus 1. That's the other rectangle, right? So if you look at this rectangle, the small one, it's definitely smaller than the area under the curve here. Who follows me? And the area over the big rectangle, it's more than the area under the curve. What is the area under something in calculus?
Integral.
So what is the integral of a constant function? Integral from this interval, right? From 1 to n plus 1 by n. That's the interval I'm integrating over, from here to here. Of a constant. This is a constant, right? N times n plus 1 dt. It's easy because this constant does not depend on t. Right? That would be very easy to integrate. Is the area of a rectangle, is this times how much the rectangle big is, right? How about the area under the curve? This f curve. What is that? That's the integral from 1 n plus 1 over n of f of x, right? We remember that from calculus? This area under the curve is the integral of the function? Integral from 1 to n plus 1 by n. All the integrals are on the same interval. That's another constant. That's just 1. Right? So how much is this integral? The integral of a constant is the size of the interval times the constant, right? So that is how much is this interval? It's n plus 1 over n minus 1, right? It's from there to there. The size of the interval here is n, this minus this. This times n over n plus 1. Smaller than, what's the integral of a function? If this function happened to be the differential of another function, if this small f is the differential of a function, there is a fundamental theorem of calculus, I'm sure you heard of it, that if you integrate the differential, you get f from the beginning minus f of the end minus f of the beginning, right? So this should be f of n plus 1 by n minus f of 1. Again, if f, how many people know that? If f is the derivative of some function big F, then when you integrate the differential, the small f, you get the difference in the integral, the primitive, between the end minus the beginning. How many people have heard of that in high school? Good. And this in here is the same, is a constant, so that is n plus 1 minus 1, n plus 1 by n minus 1, that's the size of the interval, times the constant. The constant integrated here is 1. How many people follow me? Okay, this is something that we may need to sleep on. Now, let's see what we've got. How much is this? How much is this in here? N plus 1 by n times n over n plus 1. Isn't that 1 over n plus 1? This in here, it's 1 over n, sorry. That's just 1 over n, right? It's n plus 1 over n minus 1. It's 1 over n. Times this constant, n divided by n plus 1. Who is this big F? What function has the derivative 1 over x?
ln.
That is ln of n plus 1 over n minus ln of 1. And this is 1 times, how much is this? 1 over n, right? You follow that? This in here is 1 over n, that's easy. This is the logarithm, the function that has this derivative. F is the natural logarithm function. There's only one function who has the derivative 1 over x. And this in here is the constant times the. Isn't that the same inequality like this one? How much is this? Isn't that exactly 1 over n plus 1? How much is this? That's exactly 1 over n. Log of 0 is, log of 1 is 0. And logarithm of n plus 1 by n is exactly this. Okay? So we did prove the magic. We didn't leave it as that. But we need to know a little bit of calculus to do this. Or a bunch of heavy combinatorics. This proof can be done with combinatorics, but it's super heavy. So we're done with this honor section, which is the harmonic series. That's a very good approximation to know that the harmonic series does that. So now I want to move into recurrences that we already have seen. Let's start with merge sort. Anybody remember the recurrence in merge sort? The running time. The running time of merge sort was what? Anybody remembers? Actually, do you remember how merge sort worked? It split the array in half. That's the merge sort each half, and then that's the combination. So how do we write that as a recurrence? This is the first half, doing merge sort on the first half. The other one is the other half, and doing the merging. How fast was the merging in merge sort? Linear. So this is the first half, second half. So that is 2n by 2 plus n. And we iteratively got this to, we said, there was a, if we iterate this recursion to itself, what was the answer? Anybody remembers that? Because we did this in class, right? We kind of iterated it until we figure out that the answer is n log n, right? Remember that? Well, so that's kind of like a guess. I mean, the iteration method has to be very, very tedious to be correct. Most people do the iteration just to figure out what it is, n log n. So we're going to call this a guess. And now we can say, if we got this guess, anyway, usually the guess happens through the iteration method because we force the iterations and we figure out it's like n log n. What we want to prove by induction is that T of n is order of n log n. So in these running times, we don't care about the exact values. We care it's like order of n log n, which means it's smaller than some constant times n log n. We can choose constant c. So you can choose any constant you like here because the order of this is going to be n log n.
Is it log base 2 of n or base 10?
Any log in terms of order, logs are all equivalent because they're all multiples of each other. Log base 2 or log base 10 or log base e are just a different constant.
Oh, okay.
Log base 10 of x is log base 2 of x times log base 2 of 10. So there's a constant there between logs. You can pick any log, it's going to have a different constant in the front. So again, if we do the iteration just on scrap paper to figure out, okay, it's kind of like n log n, and we need a formal proof, we can do that by induction. Here's how we're going to do it. We're going to say T of n plus 1, the induction step. This is something new. The reason I showed you is because the induction step here doesn't go from n to n plus 1. The induction step here goes from n by 2 to n. So why this works? Why can I say, before all the inductions were going from n to n plus 1, right? In here I'm saying, I don't want to go from n to n plus 1. I want to go from like 50 to 100. Would that still prove the t overall? So in other words, if I already got down t of 1, t of 2, t of 100, and then I want to do to 101, right? What I'm saying, this induction proof here is not going to go from t 100 to 101. It's going to go to some t in the middle, t of 101 by 2 to 101. The reason this is still okay is because I proved all the t's. The reasoning before was if you know t of 100, you can do t of 101. Right? That's all the proofs we've done so far. In here we're saying if you've done all of them, not just t of 100, but all of them up to 100, you can use either one of them to prove the next t. Logically speaking, at this time, I've not just done t of 100. I've done all of them. So I can use all of them if I want to. This is called strong induction. You don't have to use the name strong. Weak induction is only from n to n plus 1. Goes from n to n plus 1. Strong induction goes from all the stuff before to n plus 1. So I'm not going to use only the last one I proved. I'm going to use all of them, or some of them. Logically, still checks out. So how would I do this? I say, okay, what I want to prove is that if t of n by 2 is smaller than c n by 2 log of n by 2, I'm just stating this stuff for n by 2, then I can prove it for n. T of n is smaller than c n log n. That's my induction step. Strong induction step. Okay, so who's t of n? How do I prove this? Of course, I use the recurrence. That's 2t of n by 2 plus n. Now I use the hypothesis, the induction hypothesis. I already know that t of this is smaller than 2 c n by 2 log of n by 2. Right? I use the fact that t of n by 2 is smaller than this stuff, plus n. That is Cn log of n minus log of 2 plus n. So c, it's c, 2 times n by 2 is n. Log of n minus log of 2 is log of n by 2. And this n is this n from here. That is going to be cn log n minus cn log 2 plus n. Now I pause and I say, where am I going with this? What do I want to get? I want to get to here, smaller than this. So how far am I? This is already that, right? I just have a bunch of extra stuff. So I need to prove that this is negative. This whole thing, if it's negative, I could say this is smaller than cn log n, which is what I want. But for this, I need this whole part to be negative. Right? In order for me to say the whole thing is smaller than this term, that's essentially saying the part that's in between them has to be negative. Are we following here? Or not? We got lost. Who's following me? Oh, good. So I can choose C, remember? C, it's up to me. I can choose any C I want. But it has to be a constant. Once I choose the C, I have to stick with it. So I choose a big C to force this to be negative. I choose C equal 2. 2 times log 2, it's going to be bigger than 1, right? And this whole thing is going to be negative. I can choose the C that I like as long as I stick with it, because it's a constant. I can't choose it more than once. Everybody sees this? This is n, common factor, so this is n, 1 minus C log 2, right? That's what it is, common factor, 1 minus C log 2. If I pick a big enough C, the whole thing is going to be negative. And then if it's negative, it's smaller than this one, which is what I want to prove. So what happened here? I got a guess from iteration. That's n log n. And actually, I prove it by induction that n log n, it's a good order. As in, this is always smaller than some constant times n log n. The constant that I chose here is 2. The constants don't matter for running time. Whether it's 2 or 3 or 5 or 100, the order of it is still n log n. I want to do something. The binary search recursion is what? Anybody remember binary search? What happens in binary search? What do we do in binary search? We look through a sorted array. What do we do first?
Cut it in half.
We look at a half, right? So we have to solve that problem plus 1, because there's nothing else to do other than splitting in half. The comparison to where to go left and right takes only one operation. So how much is this if I keep doing it? If I keep iterating, this is t of n by 4 plus 1 plus 1, t of n by 8 plus 1 plus 1 plus 1, right? It's t of n by 2k plus k. In the end, if I choose k equal log n, that's going to be t of 1 plus log n. Which is what you expect. Did we know the binary search run in logarithm time? It splits in half. So what you have to do for next time is to say, okay, I got to guess that the binary search is roughly log n. Can you prove by induction that the binary search is actually log n? Like the way I did it here for merge sort, can you prove this by induction? Prove by induction. T of n is smaller than some constant times log of n for binary search.
I can help you guys out. I saw them for like 10 hours trying to figure this stuff out.
Remember, there's a recitation on Sunday afternoon, optional.
There's multiple choice ones.
You're on.
I'm free at like 3:15.
Because I wasn't sure how to help you.